we're going to discuss some example calculations using Gauss's law. Gauss's law is extremely powerful in situations that have a particular symmetry, and once you've identified that and understood that, you can use it to calculate the electric field. There are really basically three symmetries we can consider: spherical, plane and line. And I'll go through each of these. So let's first of all consider spherical symmetry. This is a situation where the charge distribution and the resulting field must have no dependence on the angles, the theta and the phi in spherical symmetry. So let's take a concrete example. We're going to consider a sphere of charge. It's going to have uniform density rho, it's going to have a radius of a, and we want to know the electric field as a function of r, so long as r is greater than a. We could of course throw in the integral if r is less than a. That would be fairly simple. I'll add that at the end, but just for now we're going to consider that. And we're going to put the charge at the origin. So we start with Gauss's law in the integral form. We have a volume integral of the divergence of E dV is going to equal the volume integral of the enclosed charge dV. And of course our volume is going to will be spherical because that respects the symmetry. So it's going to be a sphere. Again, it's going to be centered on the origin. It's going to have radius little r, which of course is going to be greater than a, as I've just said. So we have a spherical charge density, which we've put at the origin. You could put it somewhere else. That would just introduce sort of a displacement. We're going to put a spherical volume around it, and there's going to be the surface of a sphere as our surface at the outside. That should be an epsilon naught, of course. So now let's do a transformation. So of course, as always, we have that the closed surface integral of E dotted with n dA, and please note here that n is a normal vector, which I'm assuming is a unit vector. That's going to save me from writing down the hat every time. And now if we do the volume integral, of course we get a 4/3 pi a cubed, and we get a rho over epsilon naught here. And if you wanted to, you could also say that the total charge in the sphere Q is equal to 4/3 pi a cubed rho. We'll keep the full form in for a minute. So now, what do we know about the direction of the field? So the direction of the field must be radial. I'll show you why in a minute. So essentially we've taken a spherical surface, and so if we just draw a cross section, so let's have, I don't know, let's have a z and an x here, and here's our spherical surface, and let's consider a point on the surface. Now, if for instance we had the E field pointing in this direction for some reason, then by rotating that spherical surface we could change the direction of the electric field. And that would be quite wrong, because we know that we've got spherical symmetry, and so we can rotate the sphere to any position and we can't change the answer. Therefore, we need to remove that, and we need to replace it with a radially oriented field E, because that's the only direction which, when we rotate the sphere, it doesn't change its direction in spherical polar coordinates. Of course, the normal to the sphere is also in the radial direction, so n is equal to r hat. So what we're going to have when we take E dotted with n is we're going to have E in the r direction, and then n dot r is just going to equal 1. And E of r is not going to depend on the integration variables, which are going to be theta and phi, so we can take it outside the integral. So having done all of that, and it may sound like this is all rather trivial, but it's just a simple way of explaining the procedure you use in any more complicated case. So here's ER outside the surface integral dA, which of course is going to just be ER multiplied by 4 pi r squared, and that is equal to 4/3 pi a cubed rho over epsilon naught. If we divide through, and restore directions, we can say that the electric field in this situation is a cubed rho over 3 epsilon naught r squared in the r direction. You could, of course, also, if we use the definition of Q, write this as Q over 4 pi epsilon naught r squared in the r direction. That substitution is essentially trivial algebraically, which is the very well-known result from Gauss's law that if you have a spherical charge distribution, there is no difference between having a single charge at the centre of the sphere and having the charge distributed over the sphere. If the charge density is not spherically distributed, then of course you have to be a little bit more careful, and we will think about multipole expansions in the next lecture. So that was a slow and careful introduction to the spherical symmetry. We could have made the charge density depend on the radius, for instance, but that would only have changed the integral. And in this case, if we wanted to calculate the direction that the electric field inside the sphere, then we would simply have to replace the a cubed with an r cubed, and so that would change the overall shape. Let's move on to the plane. So we're thinking about plane symmetry. So now what we have is we're going to have an infinite plane with charge density, and this is going to be, of course, it's going to be a surface charge density, sigma. It's going to be in the xy plane. And we want to know, again, the electric field at a point r. Now, we can say again that, so let me just sketch a semi-infinite plane. You have to imagine that it goes on to infinity. We can say again that in this case, just putting in some axes here, here's y, here's x, here's z, E must lie along z. Now, why do we say that? Well, because this system has translational symmetry in the xy plane. In other words, we can move the plane around. We could move the point where we're evaluating the electric field anywhere in the xy plane. And so if E was pointing in any direction other than z, then by shifting the plane around, we would potentially change the electric field, and that wouldn't obey translational symmetry. Another way of thinking about it is just to consider the fact that any kind of in-plane, in xy plane contribution to the E field from one point on the surface will be cancelled out by another point in the diametrically opposed direction. So we're now going to draw our surface, and I'm going to make it a cuboid. You could make it a cylinder if you wanted to. It doesn't really matter the shape of the cross-sectional area. So there's my cuboid. I'm going to say that it has area A on the top, and it's going to have a height h. Of course, we're going to discover that that height h has no influence. So again, we say that the closed surface integral of E dotted with n dA is equal to the volume integral of sigma over epsilon naught dV. Now, if we take that volume integral, we say that that's going to be sigma A over epsilon naught, because sigma is a sheet of charge which is infinitely thin. If you had a realistic calculation, then of course sigma would have a thickness delta. You can't have an infinitely thin sheet of charge, and you would just replace the volume and that surface charge density with a volume charge density, and we would end up adding in a delta to that integral. But that doesn't matter; it doesn't change anything. What about the electric field? Well, we're going to have two electric fields to worry about. We've got the electric field above the plane, and we've got the electric field below the plane. So we've also, of course, got the sides of our surface, but the E field, when dotted with the normals to those sides, will give 0. So the only non-zero E field contributions to the surface are going to be the top and the bottom. And in each case, we will find that E and the normal vector are parallel to each other. So we will find that the surface integral of E dot n dA is actually going to equal EA, that's probably from the top, plus EA, that's from the bottom, and everything else goes to 0, and that must equal sigma A over epsilon 0, and therefore E is equal to sigma A over epsilon naught in the normal direction, and I'll put a hat on it here just for simplicity. Sorry, I've done that completely wrong. That shouldn't be sigma A over epsilon naught at all. What that should be is sigma over 2 epsilon naught in the normal direction. The A's, of course, cancel. And the normal will be plus Z above the plane and minus Z below the plane. Finally, we have the question of a line of charge, and we're going to have a density here, which is going to be lambda, and this is per unit length. For simplicity, we will assume that it's infinite, and it's going to be aligned along Z. Now, let's think about the direction of the field, because that's always something we have to do. So here's our line of charge. We're going to consider a cylinder whose axis lies along parallel to the line of charge and centered on the line of charge. And if we consider the electric field, let's say at a point here, here is going to be R, then again we say that the electric field must be oriented radially. And this is because the radial direction is the only direction on a cylindrical surface which is independent of phi, the rotational direction. And so, again, we're obeying cylindrical symmetry. You can also, if you want to, just think about the fact that for any point on the line of charge, there'll be another one, an equivalent distance on the other side, with an opposite contribution along the line of charge, and so those will cancel and only have a radial term. But actually it's the cylindrical symmetry that matters here. So we're going to say again that E is equal to ER in the R hat direction. Of course, if E is radial, then the ends of the cylinder don't count. If we had a finite line of charge, we would have to consider them, but for now we're assuming that it is infinite. So again, we have the closed surface integral of E dot n dA is equal to the volume integral of lambda dV over epsilon naught. Let's say that our cylinder is of length L, and we have a radius of our surface charge of the surface is actually R. So I've drawn this diagram wrong here. I'm just going to rework that. Oh dear, that removed rather more than I intended it to. So here is our cylinder, and we are of course considering the electric field at the point R on the surface of the cylinder, which is at a radial distance, little r. So on the right hand side of our integral we have L times lambda over epsilon naught, because L is a line density, so it's only the length of the cylinder that matters. When we consider the surface of the cylinder, the two end caps don't matter. So what we have is we have ER multiplied by the surface area of the cylinder, which is L times 2 pi little r, and that must equal L times lambda over epsilon naught, and therefore we have the standard result that the electric field is equal to lambda over 2 pi epsilon naught r in the radial direction. In every case, the basic procedure is to consider the symmetry, or if you prefer the geometry of the situation, and to think about an integration surface and volume that obey that symmetry. Once we've done that, we consider the direction of the electric field and we think about what it has to be. That then lets us take the dot product between the field and the normal vector to the surface, and from there we can solve for the field. If we're lacking in symmetry, then frequently we can't use Gauss's law, and typically what's simpler is to use the potential and then take the gradient to find the field.